traditional signal integrity SI matrix that S parameters and time domain reflectively TDR have been fundamental in analyzing interconnect loss, impedance, and reflections. However, they do not fully capture the unique behaviors of die-to-die systems in UCIe-based designs. Due to short interconnect length and complex loading effects, conventional methods fail to translate directly into multi-domain signal quality matrix, making it difficult to ensure reliable signal reception at high speed. Enter the voltage transfer function VTF, a metric that directly quantifies how much the transmitted voltage reaches to the receiver, offering a more practical evaluation of a signal integrity in UCI interconnect. Before exploring its impact on SI debugging and verification, it's important to understand what VTF is and how it differs from traditional matrices. The voltage transfer function VTF represents the ratio of received voltage to transmitted voltage across frequency. Unlike insertion loss S21, which measures power transfer, VTF focuses on actual voltage amplitude, aligning more closely with receiver signal quality requirements. It accounts for insertion loss, reflection, and loading effects in a single voltage domain matrix, providing a clear picture of how much usable signal arrives at the receiver. VTF is particularly useful in short-reach, high-density interconnects, where power domain matrices alone fail to address voltage degradation, affecting eye-opening distributions and BL rates. By bridging frequency domain analysis with real-world voltage performance, VTF enables designers to optimize equalization, channel design, and crosstalk mitigation more effectively. Given the stringent performance needs of UCI links, it becomes evident why VTF is critical for their evaluation. UCI interconnects require precise IMAX compliance to ensure robust data transmission, while S parameters provides frequency-dependent loss information. They lack a direct voltage domain interpretation needed for short-reach interconnects. TDR identifies impedance discontinuity, but does not measure eye-opening over BL rate directly. Instead, UCI specification define signal integrity requirements using VTF-based insertion loss and crosstalk thresholds, making it the gold standard for evaluating UCI links. Numerous ISSCC 2025 studies have demonstrated that S-parameter-based assessments often fail to predict real receiver performance, leading to a marginal eye-opening that only becomes apparent under voltage domain analysis. A real-world comparison of S21 versus VTF-based analysis in UCI interconnect shows that S parameters often underestimate voltage loss at the receiver, leading to a misleading SI conclusions. In a case study analyzing 3nm FinFET UCI transceivers, VTF reveals hidden degradation in voltage domain, allowing precise tuning of equalization settings to restore eye openings beyond compliance limits. Research from ISCC 2025 demonstrates that without VTF-based debugging, certain die-to-die channels fail high-speed compliance tests due to underestimated loss, and crosstalk issues. Furthermore, a major case shows that an adaptive CTOE settings optimized through VTF analysis result in a 10% improvement in receiver sensitivity and reduce power overhead by 15% compared to traditional tuning methods. These findings emphasize why voltage-based evaluation is superior in fine-tuning channel designs. As debugging effort evolve, simply identifying performance bottlenecks is not enough. The next step is to understanding how this voltage degradation impacts signal integrity metrics, such as eye diagram and bit arrays, which are crucial for ensuring high-speed operation. Measured data from ISCC 2025 UCI experiments demonstrate how VTF correlates directly to eye closure effects. A study on pallid skew correction shows that VTF-based analysis improved the eye opening width by 34%, significantly enhanced bit array performance compared to traditional frequency domain assessments. A comparison between traditional loss-based analysis and VTF shows that UCI transceivers operating at 32 gigabit per second exhibits a 61% improvement in eye width and a 56% increase in eye height after applying VTF-driven optimization. Additionally, ISCC findings reveals that using VTF to guide adaptive equalization strategies enabled more power-efficient signaling, reduced overall interconnect power by 12% without sacrificing performance. Ensuring an open and stable eye is vital. But another key concern in UCI links is crosstalk. With increased lane density, minimizing unwanted interference becomes just as important as improving signal amplitude. Traditional crosstalk evaluations using next fact-based S parameters fail to accurately predict multi-domain noise coupling in density-packed UCI links. VTF-based noise evaluation enables the identification of the previous under-detected interference patterns, leading to an optimized lane spacing strategy that reduces crosstalk-induced jitter by 60%. A recent ICC paper from Peking University demonstrated how 64 gigabit per second bidirectional transceivers benefits from a 50% improvement in crosstalk suppression using VTF-driven channel optimization. Additional findings show that leveraging VTF to model dynamic power rail fluctuation allows engineers to mitigate transient crosstalk by integrating a more robust dynamic equalization system. With crosstalk suppression under control, the next challenge is to refining equalization strategies to optimize receiver performance. VTF plays a critical role in a study on low latency UCI receivers, where it was used to fine-tune CTOE and DFE equalization parameters based on multi-domain signal tracking. The result improvement in signal-to-noise ratio led to a 20% increase in receiver sensitivity, demonstrating VTF protocol advantage in equalization tuning over power-based loss matrix. In a study from TSMC at ISCC 2025, VTF guide CTOE tuning reduced power consumption by 30%, while maintaining a 10.5 terabit per second per millimeter link bandwidth efficiency. These findings were reinforced by a case study showing that plain VTF-based calibration significantly reduced inter-symbol interference ISI in a high-density channel, leading to a 25% improvement in bit array performance. To conclude, after refining equation settings, it's crucial to ensure that UCI links meet compliance standards for widespread application. Here are summarized images showing you why the shift from S-parameter and TDR to VTF is a necessity for modern UCIe-based designs. Traditional metrics fail to fully capture voltage loss and real-world signal integrity issues in a die-to-die systems. VTF enables engineers to directly access signal degradation, optimize equation, reduce noise coupling, and ensure compliance with UCI specifications. Case studies have proven its effectiveness in debugging, verification, and compliance testing, making the must-have tool for next-generation SI analysis. Now, it's time to integrate VTF into your SI workflow, especially the die-to-die interface. Take the first step and start exploring its advantage today. Thanks for watching, and let's take your SI debugging to the next level for die-to-die interface. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.